Well, welcome back. In this session, we're going to be dealing with the process of diffusion of the gases across the blood-gas barrier. This is the second step, if you like, in the cascade of oxygen from the inspired air to the mitochondria. We've already dealt with ventilation, and now we've got diffusion across the blood-gas barrier, and that'll be followed by blood flow, which removes the oxygenated blood from the lung. Now we believe now that all the gases cross the blood-gas barrier by passive diffusion. That is to say, from an area of high partial pressure to low partial pressure, just as water runs downhill. But it's worth mentioning that it wasn't all that long ago that some physiologists believed that there was active transport of actually both oxygen and carbon dioxide across the blood-gas barrier. In fact, within my lifetime, the great physiologist J.S. Haldane firmly believed in the active transport of oxygen across the blood-gas barrier. One of the reasons why he felt that this was likely is that he was aware of the swim bladder in the fish, which is shown here. The swim bladder is the organ that regulates buoyancy in the fish, and he was aware of the fact that the partial pressure of oxygen in the gas in the swim bladder could be far above the partial pressure in the water surrounding the fish. And he was also aware that the swim bladder was a diverticulum of the gastrointestinal tract, as is the lung. And so he argued if the fish could do it, why can't the lungs do it? And how valuable that would be, for example, at high altitude, which was one of the areas he was interested in. But we now know that all gases cross the blood-gas barrier by passive diffusion, which brings us to Fick's law of diffusion, which we've already mentioned, but now we're going to look at in more detail. So Fick's law refers to the diffusion of gas through a tissue sheet. I like to think of something like a postage stamp as what a tissue sheet might be. And it says that the volume of gas per minute, per unit time, crossing the sheet is proportional to the area of the sheet. Well, that makes sense, because the larger the area, the more opportunity the gas has to get into the sheet and move across it. Inversely proportional to the thickness, and again that makes sense, because clearly the thicker the barrier, the more obstruction there is to the passive diffusion through it. Proportional to a diffusion constant called the diffusivity, which we'll deal with in a few minutes, and also proportional to the difference in partial pressure, P1 minus P2, across the barrier. Well, now, we've already seen that the structure of the blood-gas barrier in the human lung is extremely well suited to diffusion according to Fick's law. If we look at a light micrograph, we can barely distinguish the blood-gas barrier, the barrier between the alveolar gas and the capillary blood. It's right at the limit of resolution of the light microscope. And if we go to an electron micrograph, of course, we can see the barrier very clearly here. This is the thin side of the blood-gas barrier. And we can see that its thickness is only about 0.3 of a micron, fantastically thin. So we've certainly satisfied the requirement that the barrier be extremely thin. We also saw in the first session that the area of the blood-gas barrier is extremely large. In fact, in the human lung, the area of the barrier is about 50 square meters. It's about half the area of a tennis court. So we've got a remarkable feature here. We've got an extremely thin and a barrier of enormous area, and of course extremely well suited to diffusion. So that's the way evolution has provided a barrier that can work by passive diffusion. Now, if you're really nosy, here's a nice micrograph of the blood-gas barrier here. You'll notice that this is actually the last image I showed, the image on the previous slide, and the micrograph people have taken a section of it here, down here, and magnified it tremendously. In fact, I can see, maybe you can if you look very carefully, that bar is about 0.4 of a micron, fantastically high resolution, high magnification. And what's interesting about this is that in addition to the alveolar epithelial layer here and the endothelial layer here and the capillary lumen here, we can clearly see the extracellular matrix, or the interstitium as it's sometimes called. And if you look carefully, you can see an electron-dense band right in the middle of this extracellular matrix. And we believe it is this electron-dense band that contains the type 4 collagen, which is responsible for the strength of the blood-gas barrier. You see, we have a problem here. This barrier is so fantastically thin that you wonder about its integrity, particularly when you raise the pressure inside the capillaries and you raise the stress in the wall. But fortunately, we've got this type 4 collagen, which is a component of the basement membranes of the alveolar epithelial cell and the capillary endothelial cell. And in the thin part of the barrier, the extracellular matrix is actually just the fusion of the two basement membranes, and in the center of that we have this type 4 collagen band, only about 50 nanometers thick, 0.05 microns thick, but it's the lifeline which prevents us from having the contents of the capillary spill into the alveolar spaces. Now let's go back to Fick's law for a moment, and we'll talk a little bit about this factor here, the diffusivity. Now the diffusivity depends on both the characteristics of the membrane and the properties of the gases. For example, a piece of tissue is much more likely to allow diffusion through it to occur than if it were a piece of steel, for example. So the structure of the sheet is important. But in addition to that, the diffusivity depends on two factors which are shown here. First of all, we've got the solubility of the gas. Now that makes sense because in order for oxygen or CO2 to diffuse across the barrier, first it's got to dissolve in the contents of the barrier, and obviously, I would say, the more that dissolves, the more likely you are for diffusion to occur. So it's not surprising that the diffusivity is that the solubility is such an important factor, and the diffusivity is proportional to the solubility. But then we've got another term here, which is the square root of the molecular weight. In other words, the diffusivity is proportional to the inverse of the square root of molecular weight. Now, it's not particularly important, but those of you with a mathematical turn of mind may wonder, where on earth does this term come from? And the answer is that it comes from the kinetic theory of gases. If you remember back to your physical chemistry, all gases at a particular temperature have the same kinematic energy, kinetic energy, the same kinetic energy. And the kinetic energy is given by a half mv squared here, that's a constant. And if you rearrange that, that means that the velocity is inversely proportional to the mass, as shown here. So that's the reason why in this equation we see the inverse of molecular weight. Now, how do these factors, how relevant are they to the respiratory gases? Well, as we have already seen, the solubility of carbon dioxide is something like 24 times that of oxygen. So carbon dioxide has a great advantage in that respect. It's true that the molecular weight of carbon dioxide at 44 is somewhat bigger than the molecular weight of oxygen at 32, but by the time you take the square root, the difference is less. And the upshot is that the diffusivity is about 20 times greater for CO2 than it is for oxygen. So we generally believe that diffusion through tissues is going to be much less of a problem for carbon dioxide than it is for oxygen. Now let's turn to a very important topic, and that is what limits transfer of gases across the blood gas barrier. And we're going to draw a distinction between what are called diffusion and perfusion limitations. And to do that, I'm going to take three gases as examples. First of all, I'm going to talk about carbon monoxide down here. Then I'm going to talk about nitrous oxide, which is an anesthetic gas. And finally, I'm going to talk about the one we're really interested in, and that is oxygen. But first of all, let's look at the uptake of carbon monoxide across the blood gas barrier. Well, now, the first thing you may say is, isn't carbon monoxide a terribly toxic gas? Yes, it is, but we can inhale small concentrations with no problem. And as a matter of fact, later on, you'll see that we do use carbon monoxide in the pulmonary function laboratory to measure the diffusion properties of the lung. So let's suppose we have a subject here who inhales a small concentration of carbon monoxide, and his alveolar partial pressure is shown by this broken line here. The blood coming into the lung has no carbon monoxide in it, which is usually the case unless you happen to be a heavy smoker. But normally speaking, there's no carbon monoxide in the lung. And the question is, what is the time course of the partial pressure of carbon monoxide as the blood moves through the capillary? Now, you may ask, first of all, how long does the blood spend in the capillary? And you may be surprised to hear the answer to that. It's only about 3/4 of a second. So events occur very rapidly during the loading of oxygen in the pulmonary capillary. As a matter of fact, we already have enough information to predict that the time spent in the capillary would be about 3/4 of a second. Remember, we said that the cardiac output was about 5 or 6 liters per minute. If it's 6 liters a minute, that means 100 mils per second. And we said that the volume of blood in the pulmonary capillaries was about 70 or say 75 ml. If you divide 100 by 75 by 100, that is to say you divide the volume by the flow rate, you get the time spent in the capillary as 0.75 of a second. So that's where that number comes from. So it's quite clear that things must change very rapidly during loading of gases in the pulmonary capillary. So what happens when blood enters the capillary here is that carbon monoxide moves across, by passive diffusion, moves across the blood gas barrier into the blood. And of course the PCO, the partial pressure of carbon monoxide in the blood, rises. How much does it rise? Well, now you may remember that we looked at the dissociation curve for carbon monoxide before, and it's got a very strange shape. Here it is. Here's the dissociation curve for oxygen here, plotting saturation here against partial pressure. Carbon monoxide, by the way, combines with the same binding sites as the oxygen, as you may know, the heme sites. And actually, the shape of the carbon monoxide association curve is the same as that for oxygen, but the scale is greatly compressed. In other words, carbon monoxide has an enormous avidity for hemoglobin. So even at a very, very low partial pressure, way down here, you've got essentially full saturation of the hemoglobin. So what that means is that when the carbon monoxide moves into the capillary blood, the blood is able to absorb, to combine with a large amount of carbon monoxide for an extremely small rise in partial pressure. And the upshot of that is that as the blood moves along the capillary, the PCO, the partial pressure of carbon monoxide, hardly changes at all. Okay? So what limits the transfer of carbon monoxide across the blood gas barrier? Well, it clearly is not the blood flow. In fact, carbon monoxide is moving as fast as it can across the blood gas barrier the whole of the length of the capillary, because there's no back pressure essentially at all. So what's limiting the amount of carbon monoxide being taken up is the diffusion properties of the blood gas barrier. So we say that CO, carbon monoxide, is diffusion limited. Now let's look at another gas. Let's look at nitrous oxide, shown here. Again, we're going to pretend that our subject inhales a concentration of nitrous oxide. Actually, he could inhale quite a high concentration because in anesthesia, very high concentrations of nitrous oxide are given, no problem, except they send you to sleep. That's the only problem they have. So it doesn't matter how much he inhales, but we have a certain alveolar partial pressure of nitrous oxide here. Now again, when the blood enters, it has no nitrous oxide in it. When blood enters, the nitrous oxide gas diffuses across, but this time the blood does not have a high affinity for nitrous oxide. Nitrous oxide simply dissolves in the blood, and as the amount of nitrous oxide in the blood increases, so its partial pressure rises rapidly. And the net result is that the partial pressure rises so fast that within about a tenth of the time available in the capillary, the partial pressure of nitrous oxide is essentially equal to the alveolar value. And during the rest of the capillary, the partial pressure of nitrous oxide doesn't increase anymore at all. So what's responsible, what limits the uptake of nitrous oxide? Well, it's clearly not the diffusion properties of the blood gas barrier, because very early on, the partial pressure of nitrous oxide in the blood is essentially the same as that of the alveolar gas. So no more diffusion takes place over the rest of the capillary. What limits the uptake of nitrous oxide is the blood flow. And so nitrous oxide is perfusion limited. So there's a very striking difference between these two gases. These are two examples we're going to give, nitrous oxide and carbon monoxide. And incidentally, one way of determining whether a gas is diffusion or perfusion limited is to look at the difference in partial pressures between the alveolar gas and the end capillary blood. If there's no difference, then the gas is perfusion limited. If there's a large difference, as there is for carbon monoxide, or if there's any difference at all for that matter, the gas is diffusion limited. Okay, now what about oxygen? That's the important one. Well, let's take a preliminary look here. We're going to look in more detail in a moment. But oxygen is different because, for one thing, there is a partial pressure of oxygen in the mixed venous blood coming into the lung. And what you find is that if you calculate the rate of rise of the PO2 in the blood as it loads oxygen along the capillary, you find that under normal conditions the PO2 rises quite rapidly. So by the time we've got about a third of the way along the capillary, in 0.25 seconds, a quarter of a second or so, the PO2 in the blood is essentially the same as that in the alveolar gas. And therefore, for the rest of the time that the blood spends in the capillary, there's no further increase in the PO2. So clearly under those conditions, the uptake of oxygen is perfusion limited, okay? In other words, it's already diffused to equilibrium here, so diffusion is not a limiting factor. However, under some circumstances, oxygen can be at least partly diffusion limited. Here, for example, is a situation where the PO2 rises much more slowly than it normally does. So at the end of the capillary, there is a PO2 difference between alveolar gas and the blood. Now, what possible conditions could do that? Well, if there is a pathological process in the blood gas barrier. This is simply to remind us again that the normal blood gas barrier is extremely thin. We can hardly see it in the light micrograph. But look at this picture here. Here's a thickened blood gas barrier from the lung of a patient with interstitial fibrosis. In this disease, fibrous tissue is laid down in the alveolar wall. The alveolar wall is grossly thickened. In fact, I have a hard time seeing the capillaries. Here's one here, here's one here, here's one. They're not easily seen because one of the things fibrosis does actually is it destroys the capillaries. But you can see that in a case like this, you're not going to get the rapid diffusion that you get in the normal lung, quite the contrary. Diffusion in a situation like this is going to be extremely slow because the thickness of the blood gas barrier is much increased, and therefore we're going to have a problem. So we've looked at the factors that that determine whether a gas is perfusion or diffusion limited when it crosses the blood-gas barrier. Now let's take a more detailed look at oxygen, because obviously that's the gas that we're most interested in. And the top drawing here shows what happens with a normal alveolar PO2, which is 100 millimeters of mercury. We'll be talking much more about gas exchange in a later session. But take it from me, the normal alveolar PO2 is about 100 millimeters of mercury. The blood comes into the lung with a PO2 of about 40. We've actually seen that already in the mixed venous blood. Comes in with a PO2 of about 40, and under normal conditions, as I said before, it rapidly rises until it's essentially equal to the alveolar PO2. And of course, under those conditions, the oxygen uptake is blood flow limited, perfusion limited. But as we've seen, if the blood-gas barrier is thickened, we get a slower rise, and there is perhaps a little bit of diffusion limitation there, but under grossly abnormal conditions, we can get serious diffusion limitations. Now, there are three ways in which we can challenge the diffusion processes across the blood-gas barrier. The first one we've already mentioned, that is, we can thicken the blood-gas barrier, or it can be thickened by disease, and that certainly challenges the diffusion process, as we can see. The second one is exercise, because on exercise, the cardiac output increases greatly, and therefore the time spent by the blood in the pulmonary capillary is greatly reduced. And in this particular example, we're suggesting that it can be reduced to 1/4 of a second, 1/3 of the normal value. Whether it ever goes quite as low as that, I don't think anybody really knows, but that's the kind of order of change that we can expect. Now, of course, on exercise, the diffusion process is challenged because you've got much less time for the loading of the oxygen. In the normal lung, as shown here, you've just got enough time for the PO2 of the blood to reach that of the gas. But of course, under abnormal conditions where the blood-gas barrier is thickened, exercise is likely to greatly inhibit the oxygenation of the blood. And it turns out that patients with pulmonary fibrosis, for example, are likely to show a fall in their arterial PO2 on exercise for this reason, that less time is available to oxygenate the blood. Do normal subjects ever show diffusion limitation during exercise? Well, there is some evidence that they do. If you have an elite athlete at a very high level of exercise, then there is some evidence that he may show a decrease in the end capillary PO2, as evidenced by the fact that the arterial PO2 falls. But it's generally believed that that's an unusual condition at sea level, and that's not surprising. I mean, the way evolution works is that it normally gives us a lung or whatever that can cope with 99% of conditions, but every now and again you get an elite subject who is just off the end of the distribution. So that was the second way of challenging the diffusion process, exercise. The third way is to lower the alveolar PO2, and that's shown in this drawing at the bottom here. Here we've dropped the alveolar PO2 from its normal value of 100 down to half that, alveolar PO2 of 50. We can do that by taking a subject to high altitude, for example, or we can do it in the laboratory at sea level by giving him a low concentration of oxygen to breathe and drop the alveolar PO2 down to 50. Now, of course, we've got a completely different situation. First, we ought to say that the blood comes into the lung with a somewhat lower PO2. In this case, it's about 20, something like that. But you'll notice now that the partial pressure gradient responsible for moving oxygen across the blood-gas barrier has fallen from 60 here, 100 minus 40, to 30 here, 50 minus 20. So the partial pressure gradient is very much lower. What happens is that under normal conditions, the increase in PO2 is slower, and it takes longer for the PO2 of the blood to reach that of the alveolar gas. And in fact, on exercise, you would expect under these conditions that some diffusion limitation could be seen. And I should say that the best way of demonstrating diffusion limitation for oxygen in normal subjects is to take them to very high altitude and make them exercise. They show gross diffusion limitation under those conditions there. I should just add here for the purists that although it looks as though this small rise, the slow rise, is caused by the low partial pressure gradient, an exact analysis shows that the reason is an imbalance between the solubility of the gas in the blood-gas barrier and the solubility in blood, or more strictly, the slope of the dissociation curve. When we have a situation as shown here, we're operating low on the oxygen dissociation curve. You see the alveolar PO2 is 50, the blood comes in at a PO2 of 30, so we've got an abnormal situation here. So the slope of the dissociation curve is very high under these conditions. And that is the reason, and the difference between the solubility of the oxygen in the barrier, which of course is not affected, and the fact that the slope of the dissociation curve is very high, that is really responsible for the slow rise. And you can see that particularly with carbon monoxide. Carbon monoxide, there's a tremendous disparity between the solubility of the gas in the barrier and the slope of the dissociation curve, which of course is extremely steep. Okay, so that's all I think I need to say about the time courses here. Let's go on and talk briefly about the measurement of the diffusion properties of the lung. Now, frequently in the pulmonary function laboratory in a hospital, people want to know what the diffusion properties of the lung are. For example, in the patient from which I showed the thickened blood gas barrier, the patient with interstitial fibrosis, measuring the diffusing capacity is sometimes useful in the diagnosis, because if you suspect pulmonary fibrosis and the patient has a normal diffusing capacity, then that's strong evidence against it. So it's useful sometimes to measure the diffusing capacity of the lung, or the diffusion properties of the lung. Now, how are we going to do that? Well, first of all, what gas would we use? Well, clearly we're going to use a gas that is diffusion limited in its transfer. No good using a gas like nitrous oxide, because that's not going to give you any information about the diffusion properties. So we go to carbon monoxide, which is the gas par excellence that is diffusion limited. Now, we look at Fick's law, which is shown here, and Fick's law says that the volume of gas transferred is A over T times D times P1 minus P2. Now, there's no way in life that we can get a handle on the area, the thickness, or the diffusion constant here in a patient with lung disease. And so what we do is we combine these three factors into a thing that we call DL, which is the diffusing capacity of the lung for carbon monoxide, DL. It's simply a combination of those three. And so the equation reads V dot gas per unit time, is DL times P1 minus P2, and so we can rearrange that, and the diffusing capacity, as it's called, that's the technical term, the diffusing capacity for carbon monoxide is the volume of carbon monoxide transferred divided by P1 minus P2, P1 being the alveolar partial pressure, P2 being the partial pressure in the blood. But we already saw that the partial pressure in the blood is vanishingly small. The avidity of hemoglobin for carbon monoxide is such that it can take up an enormous amount of the gas with almost no rise in partial pressure at all. So we put P2 equal to 0, and that gives us the equation for the diffusing capacity for carbon monoxide, DLCO. That's the amount of CO taken up per unit time divided by the alveolar partial pressure for carbon monoxide. And that's an equation that we use extensively. You can see the units are mils of CO taken up per minute per millimeter of mercury partial pressure of carbon monoxide. Now, how do we do this? Well, the next slide just gives us some idea. It's not important to go into the details of this, but it gives us some idea of how we do it. We have a bag containing a low concentration of carbon monoxide, typically 0.3%, and the subject takes a single breath through a valve box here, and he holds his breath for 10 or 15 seconds. At the end of that time, he exhales. The first gas that he exhales comes from the dead space, so we discard that, and the second part of the gas that he exhales, we sample, and we measure the partial pressure of carbon monoxide in it. And then we have a fancy equation here that you don't really need to worry about, and that allows us to calculate the diffusing capacity for carbon monoxide. It's a fancy equation because during the breath holding period, the rate at which the carbon monoxide leaves the lung decreases because the partial pressure of carbon monoxide is falling, and so there's an exponential fall actually in the rate, in the level of carbon monoxide, and therefore the rate decreases, the uptake of CO decreases. But that can be taken into account using an appropriate equation, and so that's how we measure the single breath, how we measure the diffusion capacity for carbon monoxide. In normal subjects, it's around about 25 mils per minute per millimeter of mercury, and it can rise quite substantially on exercise. Now, we haven't gone into this yet, but in a little while you'll hear that on exercise the pulmonary capillaries undergo what's called distension and recruitment, so the area of the blood gas barrier increases quite a lot. Also, the volume of blood in the pulmonary capillaries increases, and that increases the diffusing capacity. Patients with interstitial fibrosis are going to have a much lower diffusing capacity. Normal subjects will get a big increase in diffusion capacity, perhaps a 3 times increase when they exercise, but patients with pulmonary fibrosis typically will have little or no change in the diffusion capacity. So it's a useful measurement, and it's frequently made in the pulmonary function laboratory. Now let me go on and talk about something that initially may be rather complicated, and we'll go through it slowly, and that is that the diffusing capacity, the diffusing characteristics of the lung do not depend only on the blood gas barrier itself. And we can see that by looking at this nice electron micrograph, which we've seen many times now. The distance traveled by the gas in the blood gas barrier is only about something like 0.3 of a micron, but then you've got a much larger distance into the interior of the capillary and into the red blood cell. So clearly this distance for diffusion is actually much greater than the diffusion in the blood gas barrier itself. And there's a second factor that's important here. We've been talking as though all the resistance to the uptake of a gas in the pulmonary capillary is caused by diffusion either across the blood gas barrier, or now we've added diffusion within the capillary lumen itself. But there's another resistance that I'm going to introduce now, and that is the rate of reaction of the gas with the hemoglobin. Either oxygen or carbon monoxide take a little while to react with hemoglobin to give us oxygenated hemoglobin or hemoglobin combined with carbon monoxide. And this rate of reaction can be considered a resistance that we can add to the diffusion resistance, and actually we can measure it. And I'm going to show you how we do that now. First of all, how do we measure the rate of reaction of a gas like oxygen with blood? You might say, well, I mean, surely it occurs terribly rapidly. How are you going to measure that? Well, it was worked out 100 years or so ago, a little less than that, and this is the way it was done. Here's a measurement of the rate of reaction of oxygen with reduced hemoglobin. And what you have are 2 large syringes here, and they're very strong, and they're motor driven because you're going to be emptying these quite fast here. One of the syringes contains reduced hemoglobin, and the other contains a solution with a high partial pressure of oxygen. And you arrange that both of these are emptied using a piston with a motor, emptied at the same rate, and so the products mix in a mixing chamber here. So you're going to add a high partial pressure of oxygen in solution to reduced hemoglobin. And of course that's going to result in oxygenation of the hemoglobin. And then as the solution passes along here, the reaction takes place. The solution passes along here quite rapidly, and we use a spectrophotometer to measure the increase in the oxygenated hemoglobin, because the spectrum of oxygenated hemoglobin is quite different from that of reduced hemoglobin. We've mentioned that already. Oxygenated hemoglobin is nice and red. That's why a healthy person looks nice and red. Reduced hemoglobin is blue, and a patient with severe lung disease therefore looks blue, is cyanized. So we can detect the change in the oxygenation of hemoglobin using a spectrophotometer at any particular point. After a certain time has passed, we've got a certain concentration of oxygenated hemoglobin. And so here's a plot of the oxygenation of the hemoglobin. It starts off at 0 here, completely reduced, and it's going to end up at 100% here, and this is the plot here of oxygenation of the hemoglobin against time. Well, now you can see we're well on the way to finishing the process in 0.2 of a second. So everything happens pretty fast, but things happen extremely fast in the pulmonary capillary as well. And the upshot is that this reaction time turns out to be a factor in the uptake of a gas. The reaction time can be considered as a resistance, just as diffusion across the blood-gas barrier is a resistance. And I'm going to show you an image which is rather complicated at first, but we're going to go through it carefully, and it explains the two components that we now recognize that make up the diffusing capacity of the lung, DL. First of all, what we've got here is the alveolar gas here. We've got the alveolar wall with the epithelium, the extracellular matrix, and the endothelium here. Here's the lumen of the capillary, and here's a red cell. And you see we're dividing the process, the uptake of oxygen in this case, also could be carbon monoxide. In this case, uptake of oxygen, dividing it into two processes. The one is the diffusion through the blood-gas barrier and through the contents of the capillary until it combines with the hemoglobin. And we're going to call that DM, M for membrane. So that's the diffusing capacity of that membrane. That's the physical diffusion process there. And the second is this reaction rate of the oxygen with the hemoglobin. And we're going to indicate that as theta Vc, where theta is the rate of reaction of oxygen with hemoglobin, and Vc is the volume of blood in the pulmonary capillary. And incidentally, V here means volume, and the lowercase c is used because we're talking about blood, volume of blood in the pulmonary capillary. Now, what are the units of theta? And the theta you can get from the rapid reaction apparatus shown in the previous slide. The units of theta are the moles of oxygen per minute, per millimeter of mercury, per milliliter of blood. Okay? Those are the units of theta. And if we multiply that by the volume of blood in the pulmonary capillaries, we end up with the units mils per minute per millimeter of mercury. Those are the same units as diffusing capacity. Remember, I mentioned when we were talking about measuring the diffusing capacity. So we're able to add these two factors here. And the equation we get is 1 over dl equals 1 over dm plus 1 over theta Vc. You may say, why have we got these inverses here? Because we're adding resistances. The diffusing capacity, and I won't go into it in detail, diffusing capacity is actually a conductance. It's the volume per unit time. But what we want is resistance. We can't add conductances. We have to add resistances, which is the reciprocal of conductances. Don't worry too much about that, but that's the reason why we've got these reciprocals there. Now, 2 or 3 important things follow from this. One is we can see that the uptake of a gas, be it oxygen or carbon monoxide, is going to depend not only on the diffusing properties of the membrane, but also the volume of blood in the pulmonary capillary. And so, for example, if we have a patient who's had a large pulmonary embolus and a large part of the lung has very little blood in it, the volume of the blood in the pulmonary capillaries there is reduced, that's going to reduce the measured diffusing capacity. So it's important to recognize that the volume of blood in the pulmonary capillaries is important. It was one of the factors. The other thing that this helps us to do is that we can actually separate these two factors and measure them independently, because we can operate on theta, the rate of reaction of carbon monoxide. Now we're talking about carbon monoxide. The rate of reaction of carbon monoxide with hemoglobin can be altered by changing the PO2 of the alveolar gas. If we raise the PO2 in the alveolar gas, because both oxygen and CO are competing for hemoglobin, theta for carbon monoxide is reduced. If we reduce the partial pressure of oxygen in the alveolar gas, theta for CO is increased because it doesn't have so much competition for the hemoglobin. So we're able actually to change theta, and that allows us, and I won't go into the details, allows us to separately measure the diffusing capacity caused by the physical process of diffusion and the resistance caused by the uptake, caused by the rate of reaction of either oxygen or carbon monoxide with the blood. That's a little bit complicated, that last bit, and maybe it's not important to be able to trot it all out, but I think it is important to recognize that there are two factors in the diffusing capacity for carbon monoxide. One is the physical process of diffusion here, and the other is the rate of reaction, and that the volume of blood in the pulmonary capillaries is a significant factor, and that we can also change the rate and exploit the fact that we can alter that. One last question. Is the transfer of CO2 across the blood-gas barrier ever limited by diffusion? Well, the general feeling is no. And if someone asks you, I think the safest thing is to say no. We're not absolutely certain about that. It's true that the rate of transfer of carbon dioxide through a tissue slice is very much faster than oxygen. But you know, in the uptake of carbon dioxide, as we've already seen, there are other factors involved. There are the formation of bicarbonate, the formation of carbaminohemoglobin. The rate constants for those reactions are not known terribly accurately, so we can't be absolutely certain that carbon dioxide transfer is never limited by diffusion, but the general feeling is that it is not. So let me briefly summarize the important points we've dealt with here. I started by saying that we now believe that all the uptake of gases across the blood-gas barrier, all the transfer of gases across the blood-gas barrier occur by passive diffusion. But that was not always the case. Less than 50 years ago, some people believed that active transport was important, and I mentioned the fact the bladder of the fish, which has a high PO2, which was the reason why some people thought that. I then went on to talk about Fick's law of diffusion, which is desperately important. We saw that the blood-gas barrier in the human lung is fantastically thin and has a vast area, and therefore extremely well suited to the diffusion process. We also mentioned that the diffusivity, which is one of the constants in the Fick equation, depends on the solubility of the gas and the molecular weight, actually the inverse of the square root of the molecular weight, which comes from the kinetic theory of gases. And the upshot of all that is that carbon dioxide diffuses about 20 times faster through tissue than oxygen. We then went on to look at the uptake in the pulmonary capillary of different gases. We pointed out that the blood spends only about 3/4 of a second in the pulmonary capillary, a very short time. And we looked at the time courses for first carbon monoxide, then nitrous oxide, and then oxygen. We pointed out that the uptake of the transfer of carbon monoxide is entirely diffusion limited, whereas the transfer of nitrous oxide is completely perfusion limited, blood flow limited. Oxygen is usually blood flow limited, but under certain conditions can be diffusion limited. And we went into the situations where that occurs. One is if there's thickening of the blood-gas barrier in disease, for example, interstitial fibrosis of the lung. On exercise, where the time available for the uptake of the gas is limited because of the increase in cardiac output and the short time that the blood spends in the pulmonary capillary. And finally, when we reduce the alveolar PO2, for example at exercise, then we're much more likely to get diffusion limitation. And if you want to demonstrate diffusion limitation in a normal subject, the best thing to do is to take him to extreme altitude, have him exercise very hard, and you will see it then. We pointed out, and I'll just mention this briefly, that the most important factor determining whether a gas is diffusion or perfusion limited is the solubility of the gas in the blood-gas barrier on the one hand, and the slope of the dissociation curve on the other. Rather a technical point, but that's the reason why, for example, carbon monoxide is so diffusion limited. We also pointed out that we can measure the diffusion capacity of the lung for carbon monoxide. We use carbon monoxide, of course, because it's a diffusion limited gas. We went through the single breath method briefly and pointed out that the diffusion capacity increases substantially on exercise because of the enlargement of the pulmonary capillaries and the increase in number of the capillaries with blood flow. We'll talk more about the pulmonary circulation later on. And then finally, we pointed out that the transfer of the gas into the pulmonary capillaries depends not only on the physical diffusion, but also the rate of reaction of the blood with the hemoglobin, of the gas with the hemoglobin, be it carbon monoxide or oxygen. And we looked at the fact that we can consider the uptake as occurring in two stages. First of all, the diffusion through the physical blood-gas barrier and the lumen of the capillary, and then the rate of reaction. And we pointed out that an analysis like that shows that the volume of blood in the pulmonary capillaries is an important factor in the measurement of the diffusion capacity, and also we're able under some conditions to exploit the fact that we can change the rate of reaction of carbon monoxide with hemoglobin. We can change that by changing the alveolar PO2, and that allows us to separately measure the two factors. One thing I didn't mention, I should have done, is that in some parts of the world, particularly in Europe, the term diffusing capacity has gone out of favor somewhat. People talk about the transfer factor for carbon monoxide. And the reason they do that is that, partly what I've said, that the uptake of CO is not just limited by diffusion, but particularly in a patient with lung disease, it's a much more complicated situation because you've got uneven distribution of ventilation, uneven blood flow, uneven diffusion properties in different parts of the lung. So some people prefer to say that they're measuring the transfer factor rather than the diffusing capacity. So if somebody mentions that to you, don't look too surprised. Okay, that's all we're going to talk about for diffusion. And the next session, we're going to be talking about the next step in the cascade of oxygen from the air to the mitochondria. The next step after diffusion is blood flow. And so I look forward to seeing you then. Bye for now.